はい。
Ladies and gentlemen, good afternoon. Since this is the scheduled time, we would like to now start the International Symposium, Renewable Integration into the Japanese Power Grid by 2030, a Frequency Stability and Load Flow Analysis. I am serving as the moderator for this session from REI, Shota Ichimura. First of all, as an opening remarks, we would like to have Executive Director, Renewable Energy Institute, Teruyuki Ono, is going to give the opening remarks. Good afternoon, ladies and gentlemen. Thank you very much for the introduction. My name is Ono from REI, International Symposium Renewable Integration into Japanese Power Grid by 2030. Thank you very much for joining us. And there are so many different reasons why the renewable energy has been really drawing attention. And then one of them is global warming. And just until yesterday morning, at Katowice in Poland, COP24 has reached an agreement, and that was really close. And the theme for COP24, 3 years ago, the Paris Agreement was agreed upon, and then they are to really come up with the rules for implementing the Paris Agreement, and that was really adopted at COP24. In response to that, we believe that the measures for the global warming and also the renewable energy integration will be further pursued. And various newspapers has reported on that. And I just read the New York Times article. And according to the New York Times article, and there are so many difficulties and headwinds international negotiation. And then one of the comments cited there was, indeed, there are a lot of headwinds in international negotiation, but the march of cheaper and cleaner energy technology would do far more to break the deadlock around the climate policy than any complicated treaties could. I perfectly agree with that. And one of the really background factors supporting that is IPCC, and in early October has issued 1.5 degrees report. In that, the Paris Agreement is aiming at about 2 degrees Celsius, but in order to really mitigate and the climate change impact, it should be kept below 1.5 degrees. In order to achieve that, there are several scenarios has been reported in 1.5 degrees report by IPCC, and once it is released, and then from the air, CO2 should be extracted and to CCS to store inside the underground. And in order to avoid doing that, there was some scenarios developed. And by 2030, on overall global basis, 50 to 60% should come from the renewables. And that was a scenario indicated there. And so, looking at this kind of level of the reduction, the Japanese government's target, as you may know, 2030 and 22 to 24%. And according to the international standard, this is very low. And also, in response to the request by IPCC, there is a significant gap. At least, in Japan, 30% or more, or 30%, 40%, or possibly 50% of the renewable introduction should be aimed at. In order to really integrate such an expansion of renewable energies, there are so many obstacles, and one of them is the grid connection. That is certainly one of the challenges we need to address. And in order to really integrate valuable renewable energy into the grid, and then that would be given much of the impact to the grid stability, and also in order to ensure that it will be very costly. And that is a sort of the idea widespread. So this time, and REI and Agora Energy Wende and then EGI jointly conducted studies, and also we hope that the outcome of the study and also today's symposium will serve as the important first step for further constructive discussion going forward. Once again, thank you very much for your attendance today. And I do hope that you will have the good, productive the meeting. And this concludes my opening remarks. Thank you very much.
The next is a keynote speech. We have Mr. Gunta Scheibner, the Senior Advisor of IDEA Grid International and former Director of System Operations of 50 Hertz.
Also from my side, hello to the auditory. At first, I would like to introduce myself. I have an experience of 42 years of system operations. I started my work life in 1977 as a dispatcher in a control room and finished my work life on the 31st of October in 2018. And now I'm a senior advisor at EGI to transform or to transport these lessons learned from the integration of high shares of renewable energies into a grid, into a system, and the influence of renewable energies to the system operations. 50 Hertz is one of the 4 German TSO. In Germany exist 4 TSO, and we are located in the highly meshed, in the highly interconnected grids of Central Europe. And this highly integration, this highly interconnection is one of the main success factors to integrate high shares of energy, high shares of renewable volatile energy. To be able to import and export energy is one of the main topics, main factors. The main figures of 50 Hertz you can see here. The red colored are the main important figures. We are a low load area of Germany. Only 1/5 of the load of the final consumption are located in the area of 50 Hertz. But we have integrated in our system, we are connected to the grids inside of 50 Hertz, 31 gigawatts of renewable energies, and thereof 18.5, 18.6 gigawatts of wind onshore energies. The infeed from renewable energies in the system or inside the control area of 50 Hertz reached 51 terawatt hours in 2017. And the biggest share came from the wind onshore, 56.4%. The second biggest share came from biomass, 21.7%, and the third from photovoltaics, 17.9%. We talked about the governmental targets. The German government sets a target to reach 65% of renewable energy integration in 2030. It's for the whole Germany. 50 Hertz area, the area of 50 Hertz reached 53.4% in the year 2017. We will reach this goal of 65% in between 2020 and 21, much earlier than the government set for the whole Germany. So whole Germany reached currently 36%. In 2017, we reached 51 days with higher infeed from renewable energies than load or final consumption in the control area of 50 Hertz. It is a growing share because the development of renewable energies is still expanding, extending further on. Often I heard the question, is it possible to operate a system in a secured way and the quality of supply can be secured with a high infeed from renewable energies? You can see here on the graphs that we have a quite good criterion, or we reached good criterions, and I think it still works, not? Germany reached 12 minutes of interruption of supply of the final consumers. 12 minutes, the lowest value for the whole Europe especially, and with the highest share of renewable energy integration. I think it's a good signal that it's not a problem to integrate renewable energies, it's only a challenge. For all the engineers, it should be a challenge to integrate more and more of renewable energies to fulfill the energy transition at least. These pictures, I like them because it shows what was happening in Germany starting in 2000 and not finishing in 2017. At least we reached currently, on the end of 2017, 49.6 gigawatt installed capacity of wind and 42 or you can say 43 gigawatt of PV, with a growing, almost growing development of these two energies for the next years. And especially for the area of 50 hertz, we are with a low density, much lower density of population than in the rest of Germany. And so we have more and more big parks of PV, installations of big parks of PV, and also bigger parks of wind energy production. I heard about the biggest project in our area, 300 megawatts of PV to integrate with an option up to 500 megawatts. It is one power producer of PV, and I think it's a very challenging situation also for the TSO, because currently 97% of the installed capacities are connected to the lower voltage levels, to the DSO voltage levels, and only 3% are connected to the TSO levels. So we have another challenge for the interaction between TSO and TSO. On this slide, you can see what will be happened during the next years. In 2017, as I mentioned, we reached 31 gigawatt installed capacity of renewable energies in the control area of 50 hertz. And until 2030, we will reach 45 gigawatt of installed capacity, mainly coming from the additional installations of onshore wind and PV. Onshore wind, not more installations, but coming from repowering, changing the older turbines and using the newer turbines. The older turbines reached 1.5 megawatts, and the newest turbines reached 7.5 megawatts. And in the future, we also will have 10 or 15 megawatts turbines. One turbine, 10 megawatts. 10 years ago, I couldn't imagine to have such a turbine as an installation in the grid. But currently, 7.5, you can visit them in our control area. The next question is how to operate a system, how to balance a system, how it works together, how it fits together with a high share of renewable energies. And I think it's the same situation as it is here in Japan or everywhere in the world. You have a primary control, you have a secondary control, you have a tertiary control to balance the system for security of the stability of the frequency as one of the main quality parameters. And in our situation, almost also we have the same figures as a real TSO without own generation. And we have to organize a market where we can tender the necessity of capacity from the generators or from the consumers, why not, to secure the frequency control. And maybe you have heard that in Germany we will stop all the nuclear power plants until 2022. And we also started the discussion about to stop the conventional power production based on lignite. And mainly the secondary control, the fast control, comes from the conventional power plants, from the lignite-fired power plants. And so we had to think about what will be happen during the next years, also in relation to the PV installations and also to the wind installations, where the energy or the power, necessary power, can come from. And so we have clearly or analyzed that it is necessary in the next years, during the next years, much more to integrate the renewable energies also into the control power market. It is absolutely necessary to integrate them. And the dependency on the necessity of control power, depending on the installed capacity of photovoltaics, you can see here on this graph, and it's obvious that it is necessary in the next years, especially the forecast of 2035 and the forecast of 2050 shows it very obvious. And of course, we had to think about who can be partners to offer on the market, on a balancing market, products to control the frequency. We have identified and we have integrated into the market, as an example, these four types of control power providers. We have so-called electric boilers installed in district heating systems where they are using gas-fired CHP to boil the water or to produce the heating. And in cases we have too much infeed from wind, higher than the consumption is, we can use the energy not used for consumption to switch on these electric boilers to heat the water instead of gas by electricity. And the next one is battery, usage of batteries for primary control. They are very fast, they are excellent, usable for primary control, and we have installed in our control area several units, 1 megawatt, 5 megawatts, and 10 megawatts, and there are options or projects to install batteries 80 megawatts, and somebody talked about 6,000 megawatts. To use them not only for primary control, but also for balancing and for congestion management. The third one is so-called mini CHPs. Mini CHPs installed in the cellars of houses, which can produce electricity and heating. And they offering to the TSO also via a so-called virtual power plant, 5 megawatts for secondary control, we are using them. And last but not least, the aluminum production is using high share of electricity, and they also can offer primary control for the TSO purposes. These four examples shows that the diversity of the partners will increase in the future, and we will have a lot of more partners and actors on the control power market. In 2015, in Europe, we had a solar eclipse. And the solar eclipse, not a full eclipse, but only the shadow was on the whole Europe, covered the whole Europe. And the question was, how reacts the PV if the shadow comes and the shadow leaves? And on these curves, you can see what was happened. The shadow comes up. We lost 6 gigawatt of infeed from PV, and the shadow leaves. We got back doubled 13.7 gigawatts of additional infeed. In between, the lack of infeed from PV was covered by conventional power plants, and we have seen during the eclipse gradients of changing the energy infeed from PV 4 times higher than we have them every day when the sun comes up and the sun goes down. So, and this gradients showed us the situation, how it will be during the next years in 2035, when we will reach higher installed capacities of PV, and then we will have the same gradients we had during the solar eclipse every day. And the question was, is it possible to operate the system? It was a live test to the whole Europe electricity system, and it was very good possible. We have absolutely accurate, balanced system, operated the system. The frequency was absolutely stable. It is not a problem for the operation of a system with an installed capacity of much more than 40 gigawatts of PV. The cooperation between the different partners, the cooperation between the different TSO, it was one of the biggest questions during the last years. And as I mentioned, the TSOs in Europe are highly interconnected. And of course, everything what has happened in one area of a TSO will influence the other area of the TSOs in Europe. And so we started to cooperate, closely cooperate in 2010 inside Germany. And the question was how to balance the system. In the former time, every TSO had to balance his own system. And starting from 2010, we balanced the system together. Before using the secondary control, we used the differences in the balance of the other system. And this leads to a very successful project for interaction between the TSOs, between the different TSOs. As you can see, all the surrounding TSO of Germany joined this principle and joined that method. And what was the result? It is very good, seeable on this screen. The use of the control power reduced tremendously during the years beginning from 2010 until 2017. But the integration of renewable energies grow tremendously. So it is like a paradoxon, but it's obviously for the German situation and for the European situation. It was my last slide. Thank you for your attention. And in the discussion, I'm ready to answer to your questions.
We would like to move on to the presentation of the research report. In terms of the summary, Ms. Mika Obayashi, Director of Renewable Energy Institute, she is going to give the overview of the report.
Thank you. I'm Obayashi from REI, and today, thank you very much for joining us here for a presentation of the research results. Today, in your handout was study report and preliminary translation and summary has been distributed to you. And once again, we are really going to have the full translation version on website and also the executive summary itself. We are going to arrange the layout and to really disclose it on the website eventually. And today, what I'm going to introduce about the study and the demand analysis and Mr. Tatsuya Wakayama of the Senior Research Fellow of the Renewable Energy Institute, and Mr. Peter Melk is going to talk about the grid stability study result and why together with area energy BEMDE and EGI, and we really jointly conducted this study, and so I'd like to refer to the reasons why we have embarked upon this. And this is a mixture of both Japanese and English, and it's kind of very busy on slides, but I'd like to really use this. And in presentation, all these presented materials are really going to be uploaded on our website, and also we are really videotaping at the session, and so you will be able to really take a look at it on demand. And so I hope that you will make use of it. Now, first of all, I'd like to really talk about the growth of the renewable energy, and always, as usual, this is the slide I am really going to using. And we have seen the very rapid expansion of the global the renewable energy, and already it is almost coming close to 400 gigawatts in the PV, and lately after 2012, and it exceeded 100 gigawatts, and already in 2016 it went over, and then last year it exceeded 300 gigawatts, and also in last year and 400 gigawatt was exceeded, and probably by the end of this year we may really go over 500 gigawatt and 42 gigawatts. This is the sort of the PV expansion in Japan as of the end of last year, and because of the FIT scheme, has really pushed this on the growth. Now, this is the wind generation overall, and 540 gigawatts, and the very competitive energy sources. It has really seen much of the in-feed, and this time, because of the larger scale and also the offshore, the wind generation has been driving this growth. And Japan's capacity expansion at the bottom, it's difficult to see, and 49 gigawatts of the PV, and in case of Japan, wind is lagging behind, and only with 3.4 gigawatts is the capacity available now, and so it is still small. And there are various reasons behind this, I believe, and on our part, the major reason is the wind generation cannot be really connected to the grid, and that has really hindered the growth of this particular energy source, and that has really halted the growth of the particular industry. Here in Japan, 10 major EPCOs are operating, and then they are to really ensure the demand and the supply balance. And in 2016, they had this retail free market, and so they will be able to really go into the other control areas, and this has been very active nowadays. But as with adjustment of the supply and demand, it should be done within the area or the region, and so this how to really make use of this inter-regional sort of collaboration and cooperation should be the key. And as you can see, Tokyo is the largest demand is 65 giga, and Chubu 33, and Kansai 37 gigawatts. And so all these three really central three major demand areas. And in Japan, we have seen the growth of the PV's generation, and in each of the regions, for example, this is Shikoku, the electric power company, and 100% or more of the demand has been able to be accommodated by the renewable energy, and so 73% of the PV and 3% wind, and so variable renewable energy would account for 76% of the total demand on a certain day. And this is a little difficult to understand, but within the supply area, and the maximum is the in-feed of the renewable energy when it was recorded. And Mr. Kimura Keiji of the senior fellow has really been disclosed this information. So I hope that you will visit our website for further details. Not only Shikoku, but for example, as you can see, Hokuriku and 94%. The renewable energy was the sort of energy source on a certain given day, and Kyushu and 69% it has really covered the total demand on a certain given day in Kyushu. And Kyushu, as I have shared with you, and 19 gigawatts is the large demand in that region, but the 90% or so of that demand is being satisfied by the renewable energy. And Tohoku, and 18 gigawatts over here. And to tell the truth, in Tohoku, 86% is coming from the renewable energy in a given day, in a certain day. So looking at the global trend in 2050, more than 50% it can be supplied by the renewable energy. And also, as Scheibner-san has already talked about the German target, and 65% is the government target in 2030. And already, the executive director, Mr. Ono, has touched upon the Paris Agreement in EU. And 2050, the carbon neutral needs to be achieved, and that is sort of the goal in their vision. And so, in that context, at least as far as the electric power is concerned, and the future of the 100% infeed by the renewable energy should become visible both in the world as well as in Japan. And from 2010 to 2017, and how the world change, what kind of the changes have been seen in electricity generation. And in the last 8 years, as you can see, nuclear power has really been dropped to almost zero. And then, the demand, as you can see on the very right-hand side, is declining. And the power source, the gas and PV has shown a significant growth. And looking at this trend, gas or the PV as well as wind is showing a little small growth. But with the increase of the renewable energy, we are now seeing this variable renewable energy taking more of the proportion. And however, on the other hand, in case of Japan, as you may be well aware, energy basic plan is in place, and the target has been set for the renewable energy, and 2015 it was set, and once again the same target was decided by the cabinet ordinance, and according to that, and in 2030, 22% to 24% should be supplied by the renewable energy source. And back in 2015, we had a very big discussion on that point, and if we are to really promote our energy saving and also the lower energy consumption, and as we accelerate the use of the renewable energy in 2030, 40% or more of the renewable energy can be really achieved. And so that's the discussion we had on an Excel basis. We had conducted various calculations, and furthermore, as we have been using Wakayama-san's the demand study was used as a basis, and the government target remains unchanged. However, during the course of the discussion, and 40% of the renewable energy, and particularly variable renewable energy, can be really fed into the grid or not, and that kind of discussion has ongoing. And in case of Japan, the renewable energy and the VRE, and particularly of wind and PV, and it's unpredictable, and it will really give much more the negative impact to the grid. And as we have more of the renewable energy, then the equivalent amount of the thermal power plant generation that would be necessary. And also there is a limit to what renewable energy can do, and renewable energy cannot really accommodate all the demands for the industry. And then on the heavy industry demand cannot be satisfied, and always on TVs, this kind of the argument has been really made. But already 37% of the demand is satisfied by the renewable energy in Germany. And also there are some countries where renewable energy is accounted for almost 100% of the demand. In order to really promote the discussion on this, and we would like to really demonstrate a rationale behind the use of the renewable energy based upon the grid analysis, and also grid related information is not being made available to the public, and even us think tank cannot really make an access to the very in-depth information related grid. And so we would like to really promote the disclosure of more of the grid information, and also relevant to that, we would like to really promote the transparent discussion. That is the reason we have decided to embark upon this kind of study. And in Japan, the advanced insights or this, based upon the experience, we cannot really demonstrate what can be possible. So we have decided to do the joint, the international collaboration, and then together with the Araga Energy Wind and this Area Grid International, which is really being conducting the international project. And so we have decided to work together with them this time. And going forward, Mr. Tetsuya Wakayama and Mr. Peter Melk, who have really led the project, are going to really give the findings of the studies. And then because of the great studies, it is very technical. And then in the Japanese version, at the very end, glossary is attached. But even then, you may really come up with lots of questions. And so after the study introduction, we were going to have the panel discussion, and we would like to have time for Q&A. So we would like to really ask your active participation to address many questions, so that we will be able to really go one step ahead from the current study. So we now would like to really go into the introduction of the study.
Next, I'd like to call upon Mr. Wakayama, Tatsuya Wakayama, the presentation 1, the Associate Professor, Global Energy Research Alliance Unit, and Kyushu University Senior Research Fellow. Thank you for your kind introduction. As was introduced, Senior Research Fellow at Renewable Energy Institute, Rei Wakayama. I'm also the professor at Kyushu University Platform for Inter- and Transdisciplinary Energy Research. Allow me to share with you the result of the grid analysis that we conducted. This shows the methodology overview of the analysis. It's a three-staged project. First, scenario development, designing the scenario. In 2030, what kind of society do we envision? What kind of power mix? To determine those factors, we built a database. So 2030, the forecast for installed capacity distribution of renewables, we collected information in that regard. Based on that scenario, dispatch modeling was conducted. Regarding this dispatch modeling, in 2030, on a certain given day, by hour, the demand-supply structure in each region, the balance of the supply and demand is simulated under this dispatch modeling. By this, on a certain given day in 2030, how much renewable energy can actually handle the demand. In this simulation, the renewable energy ratio can increase on a certain day. On that day, when the ratio of renewable becomes high, what would be the possible impact on the grid? We did that in the last one, grid modeling, namely. In the analysis of the grid modeling, impact on the frequency was looked at. When the renewable energy ratio goes higher, the conventional the supply of the inertia, the ratio of the conventional energy becomes lower. And then to maintain the grid frequency stability might be affected. Those are possible concerns. So to those concerns, is the stability ensured sufficiently or not? That is what was looked at under this grid modeling. In this grid modeling, we also analyzed the load flow. It's available in the summary. Please take a look at it when you have time. So three-staged analysis was conducted, and when the more renewable energy is used, what would be the possible countermeasures that we could have? First, about the scenario development. In 2030, we looked at two scenarios. One, as Ms. Obayashi mentioned, government target scenario based on long-term energy projection by government. So variable, the VRE, the PV, 64 gigawatts, wind, 10 gigawatts. Those are the assumptions under the government target. The second scenario is a higher renewable energy scenario. We did this one as well. PV and wind, based on the industry associations, the targets PV 100 gigawatts, wind power 36 gigawatts. These are the assumptions. If you look at the left, you must be familiar with this. This is based on long-term energy projection, the FY 2030. This is just for your reference, the energy mix. Here, 7% PV, 1.7% for wind. Now, higher renewable energy scenario, based on the industry, the trade association's targets, this is the higher level of renewable. In 2030, in which region, what the power generation facilities will be available? You can see the distribution on the right-hand side. FIT and the approved facilities and the ones that are already existing are looked at as reference. According to this Tohoku area, large-scale wind installation is expected, and in the Kyushu EPCO area, the significant PV could be introduced. Those are the things that you can see from the right-hand side. Based on the scenario, the next demand-supply simulation was conducted, dispatch modeling, namely. In this dispatch modeling, U.S. California, Berkeley, renewable energy appropriate energy laboratories and others developed something called switch model. We used that model. Regarding the switch model, this is open source, the optimization of demand and supply, and also software to optimize long-term demand supply plan. There are 9 EPCOs in Japan, demand of those areas, and the operation capacity of the tie lines, interconnectors, are looked at. In each region, in each hour, what would be the actual balance, demand and supply? It is to optimize the cost. So this is just an example, some examples from the computation results. On a certain day, simulating demand and supply in Hokkaido, light blue, that the wind power generation output is high, and in middle, the gas fired, the purple is high. In Kyushu and others, the PV is significant. In Shikoku, PV is significant in terms of its potential. But as a reference, the MET information in Shikoku was not really good. So in Shikoku, coal-fired thermal power generation output is high. So by region, by hour demand supply and renewable energy output data was used, including existing ones, optimization of supply and demand. That's how we did the dispatch modeling here. You can see some negative direction. So this using the tie line into other areas, there's the exchange, and also pumped hydro is shown in the negative direction. So this is the simulation dispatch modeling. Japan as a whole, if you look at this is integrated demand and supply balance of the entire Japan. 2030 on a given maximum demand day, minimum demand day have been picked up. On that particular day, curve of demand supply from April to the next March next year, you can see that in this chart. According to the government, this is the demand supply at the government target scenario. So based on this government target scenario, variable VRE, the instantaneous VRE penetration reached up to 42%. That's the government target scenario. So the 100 PV, and in this higher renewable energy scenario, this is the result. Wind 10 gigawatt PV, the 64. PV 100, wind 36. So you can see that light part during the winter, that the wind power generation is also significant. The VRE, PV, and wind, as their introduction increases, and then the instantaneous VRE penetration could reach up to 72%. Some characteristics. This shows just a ratio. Actually, when the demand is small, so May or March, when the demand is low in a certain hour range, PV and wind generates, then this ratio could go up higher because the overall demand is low. On the July and August, when the demand is high, PV and wind, while their supply volume can be high in terms of the ratio, it's not that significant. So in the demand and supply patterns, renewable VRE supply ratio could high and on the stability of the grid and the grid frequency, what could be the impact? That's what we calculated using the model, grid model. As a basis, the IEEJ already built their model and power system model. We used that IEEJ model. 2001, it had already been built by 2001. Regarding that information, we used the power factory to validate this model. And 2030, as a power mix, if there are any changes, what would be the possible impact, especially focusing on frequency? We conducted analysis. Possible impact on frequency, to be more specific, in the grid, when the ratio of renewable energy becomes high, 1.5 gigawatt, if there is the generation loss of that much, what would be the changes in frequency? How can they be restored to the stable situation? That much has been analyzed. This is the result. In the executive summary, this information is available as well. You can see some lines. So when there is an incident, accident, with that, the loss of generation, there is a lowering of the frequency with the other operating power plants. By their controlling power, how best to restore the frequency. To that end, how much time is required, to what low point the frequency can actually go down. You can see some colors. Light blue, VRE, the ratio is 9.4%. Pink represents VRE 44.8%. Purple, 49.1%. Green, 64%. VRE ratio, when it goes up, for instance, when the conventional power source, the ratio of those conventional power plants that handle the frequency response becomes lower. So with the higher ratio of VRE, until the restoration of frequency, the amount of the droppage of the decrease, you can see that until it's restored, the time until the restoration becomes longer. Between the west and the east parts of Japan, we conducted the calculation. This shows the Western Japan result. Also, you can see three dotted lines. Regarding the dotted lines, from the renewable energy, the frequency control capacity was not conducted. If there is any the loss of power generation, what would happen? But in the West, as a parameter, the 58.8 hertz decrease. This is the kind of a threshold. Going down beyond that, by shutting down the load, the frequency has to be stabilized. Otherwise, it could lead to the large-scale blackout. With no measures, renewable energy, when it goes up to 64%, then there is a risk that the frequency could go down below that threshold. The green, with PV and wind power generation, if they could offer that frequency control capacity, what could happen? In other words, the conventional power source frequency control service, not just on top of that, PV and wind power generation, if they can offer the frequency response, FFR, fast frequency response, then the lowering of the frequency can be maintained above the threshold of 58.8, and that was indeed the result. In the west and the eastern part of Japan, we conducted that analysis, and these are the results. The frequency, lowering of the frequency, is it in the tolerable range, or does it go to the critical range? So with the higher range of instantaneous the penetration of VRE, you can see this. This is the western part of Japan, the wind power and the PV, the FFR. Without the FFR, it could go down below the threshold, but by using the FFR, it can be managed to be within the tolerable range. Similarly, we did the analysis in the calculation of the eastern Japan. In the eastern Japan, the tie line between the east and Japan, HVDC, was used for FFR 600 megawatts. By providing 600 megawatts using that connection line, essentially, with the high VRE, it could actually have an impact on the threshold, but with the HVDV FFR, that the decrease perhaps could be contained within a tolerable range. These are the results. As we have one message, going forward, VRE ratio goes up. Then, when we think about the grid stability, by our instantaneous VRE ratio, in terms of that ratio, to what extent it can be raised. In a way, this could serve as a kind of a threshold for us to have a discussion on the stability. So in order to increase that so-called threshold, VRE, such as PV and wind power, by using them, we could perhaps use them to offer FFR service, fast frequency response. 60% in the Eastern Japan and Western Japan, 70% when the renewable ratio reaches 70% or 60%. Then, if you increase this to VRE more, and should there be any stability risks, if you go beyond that, curtailment is one measure to address that issue. For instance, as a result of our computation, the VRE in East Japan 60%, in the Western Japan, if it goes higher than 70%, if there should be any stability risks, if you go beyond that, curtailment can be introduced as an assumption. As a result of the dispatch modeling, if renewable energy expands, and the government target higher than that, and if it reaches 33% per year, the VRE reaches 23%. If you go beyond that threshold, curtailment can be conducted. We conduct computation. It's about 1.8% per year in terms of curtailment volume. There are some forecast errors, and we need to validate that more. Then this curtailment volume could increase. So instantaneous the penetration ratio, if it can increase, then the total annual curtailment volume can be lowered. That's one of the results. In the Western Japan, 70%, East Japan, 60%. Regarding these threshold values, renewable energy expands further, 40% per year, 29% VRE. Even if it's reached, the curtailment is likely to be about 4% or so. So Japan, as one particular target for us to achieve, I think this is the level that is worth considering. As you can see, according to a calculation, while there have been some discussion on the government about the disclosure of the grid related information, we are third party. We have been using whatever is available. By doing this analysis based on the quantitative discussion, we can activate these discussions further. Next, Peter will talk about this grid analysis in more detail. So much from me. Thank you so much for your kind attention.
The next presentation is to be given by Mr. Peter Merck. It is about grid stability analysis. Mr. Merck is a power systems expert of Power System Operations and Security of ERIA Grid International.
Thank you very much, Tatsuya, for your presentation. I will, by the way, I'm surprised that we have such a large audience. I'm very delighted to see so many people which have an interest in our study and in renewable integration in general. I would like to pick up a little bit on where Tatsuya left, focusing a little bit more on the analysis of the grid study itself. So, is everything in Japanese? Yeah, okay. I think I will manage. So the objective of our study was, finally you have learned we have had a look into two scenarios, the official governmental scenario and a little bit more progressive scenario in terms of renewables. And one major objective was certainly to investigate a little bit how can renewables participate in auxiliary services or specifically in frequency stability. So let's move on a little bit and have a look what does it mean, stability. Usually you have a very constant frequency of about 50 or 60 hertz. This is when nothing is happening. But as you know, unfortunately in Japan you sometimes have earthquakes or other incidents which might cause eventually a loss of generation. This doesn't happen in Japan only, this is basically everywhere in the world. And you need to be prepared for situations where you have outages of huge power plants. So in this case, in our scenario, we looked a little bit into the situation where we have a loss of 1.5 gigawatt generation. And according to our study, this is what would happen. You see the frequency drop quite rapidly within the first 10 seconds. Frequency goes down to about 58.6 hertz, which is in our case below a critical threshold, which we defined at 58.8 hertz. Maybe one sentence why we defined this threshold, because if you go further below, there might be a chance that you have further disconnection of customer generation, and this is the last thing you want in such a situation. So in this case, the event would be critical because you go below the threshold. So we thought, okay, how can we improve this? And therefore, I would like to highlight a little bit this picture. This is an example from Ireland, from Enercon wind turbine, at which such a similar event was simulated. And you see what happens. When the frequency goes down, the wind farm is injecting additional power to support the grid. This is a feature called fast frequency control, which is commonly available. So this is no new technology. You can simply buy this not only from Enercon, but also from other manufacturers. And this is exactly what we need in such kind of events. So the key message here, which I want you to take away, is that renewable energy sources can provide other services than providing energy only, and really make a difference in such kind of events. This is very important to know. So we implemented this feature in our model, and in this study case, you see, by employing some 250 megawatt of fast frequency restoration reserve, which is actually acting quite fast. Within half a second, you have the power you need. You can make this event significantly less critical and actually move up to a frequency drop which is probably still acceptable. So this is one major outcome of the study, which I wanted to highlight a little bit. And on the next slide, I want to take this a little bit further and have a look into the two synchronous areas. So in this representation, you saw it earlier from Tatsuya and a little bit another graph. You see on the one hand side the shares of renewables, and you see different situations with different shares of renewables. And on this axis, you see the frequency. It's now in per unit. So 98 would represent 49 hertz or 58.8 hertz. And we extrapolated a little bit this curve to see where we end up. So when we take our critical threshold and we move over, we get a crossing point here, and then we can find the shares of renewables which we can handle. And you see you end up at around 60 to 70%, depending on the exact conditions and the exact support of the renewables. A little speciality is this plus sign here. So for the Eastern Synchronous Area, we also incorporated the case where the interconnection between the two synchronous area, the DC interconnector, is also used to support the control area where you have the event happening. And now moving on to the next slide. Let's leave this stability topic a little bit and look at the results of the load flow situation. So the idea was now to investigate how do the load flows evolve in each area when you increase the share of renewables. Obviously, this depends a little bit on where you put your renewables. We have made an approach where we upscaled the values or the distribution where we have today to our future scenario. And as a further speciality, we said, okay, we look at the meshed lines. Meshed means here a line like this one, the red one, which is inside the network, and not call it feeder line, which is at the end of the network. Because I mean, here it's quite obvious if you have huge renewable generation here and you increase it, then this transmission line probably gets more loaded. So that's we focused on the lines which are really mandatory for the energy transportation to other areas. And surprisingly, you see here, okay, in some areas, the general line loading of these mesh lines is going up. But also, and this is what you maybe didn't expect, that for some control areas, the loading goes down with a higher share of renewables. And this is simply due to the distribution of the renewables. If you place them closer to your load centers, then you can reduce the need for energy transport, and you might end up with this results. So, message to take away from here: the distribution of renewable is key, and you see this also in the German example. Some of you might notice the north-south problem. A lot of generation in the north, renewables, wind, a lot of industry in the south. You have a huge need for transport. So maybe we should think in Germany also to start placing more renewables in the south. I don't know. Finally, we also investigated a little bit on reactive power, which is a rather technical topic. If you're not a power system engineer, you have probably never heard of it. But for the system operation, this is quite critical. You need to take care of this as a system operator. And again, before I explain this table a little bit, I would like to highlight my key message from before. Renewables can provide other services than purely energy only. For example, providing reactive power. And again, this is a standard feature. When you look at wind turbines, you usually get this light gray curve as a default feature, but you have upgrade features for more reactive power provision. So when we now go to the table, this table shows you in snapshots with higher shares of renewable. Yeah, when we really go to these extreme cases of 60 or 70%, of course, a lot of thermal power plants like coal might be displaced, which originally provided this reactive power. And we're missing some reactive power. So this is MVR, megawatt reactive. But it's actually not that much. In this case, it's around 2 gigawatt reactive. Why I'm saying this is not much, because when you look at our assumptions of 100 gigawatt of PV and 63 gigawatt of wind installations, you can easily handle these numbers with renewable energies providing reactive power. And by the way, this is also happening in many countries. And now I'm concluding already my little presentation. So we tried to derive some recommendations which we can give, or some findings. And we split it into 3 parts. So we said, okay, what can the policy do, or the regulating bodies? What can the system operators do? And also what can the renewable developers or the renewables itself do? I mean, first of all, from a policy side, you need a framework for renewables to provide other services. Because if, for example, if nobody pays you for a feature like this, then nobody provides it. Unless you make it mandatory in your grid codes, then it's a different story. So in this case, the policymakers can create a transparent and non-discriminative framework, for example, establishing a market for fast frequency response services. This idea is not one of mine. This is also happening, for example, in the UK or in Ireland or in Texas. So this is common practice already. Secondly, going to the system operators, they should a little bit get away from the viewpoint that renewables causing trouble. If it gets too much, you can't handle it anymore. You have to really make them part of your auxiliary service portfolio, saying, okay, these technologies can provide different services than pure energy. Why not use them? Because if you have more providers for this kind of services, maybe also the prices go down, which is also quite wanted or a good thing, so to say. And last recommendations for the renewable sources itself, or the developers or operators. You have to anticipate the grid's needs. This means operating a power system is much, much more work to do than just managing energy flows. You have to handle control power, you have to handle frequency stability, you have to look at your voltage levels and reactive power flows. And you should get into this thinking and also develop solutions to participate in overcoming or facilitating the integration on that levels, which is where technical solutions are available, so why not use them? And by that, I would like to come to an end, and thank you very much.
This concludes the presentation of the outcome of the study this time.
はい、皆様。
Thank you for waiting, ladies and gentlemen. This is time to start the second half session, and we are really going to have the panel discussion. And before we start the panel discussion, and from the panelists, well, we would like to ask each panelist to give their presentation first of all. And from Agora Energy Bunde, Senior Associate, Mr. Dimitri Pesia, please.
Thank you very much. I'm very glad to be here, and I'm also very glad to have done this project together with our colleagues from Renewable Energy Institute. I would like to thank them once again, Mika Obayashi, Tatsuya, Shota, and the whole team. I think it was a very exciting project, at least for me, with the help of the consultant from Germany, so Peter and also Stefan, who could not come here today. Thanks a lot to everybody. I think just before we start the discussion, I wanted to reflect a little bit on what are for me the main learning of this study and how it can be applied for moving the transition in Japan. When we speak about grid stability in Europe, I have to say it's not so much an issue or concern today, except in very small systems like maybe Ireland. But globally, we have already a lot of renewables in our systems in Europe. In Germany, for example, in terms of production, we have about 22% of wind and solar, so variable renewables. Now, the difference obviously is that we are interconnected. And when I'm in Japan, always this is what I hear from people saying, yeah, Japan is different. It is a bit different, but it's not completely different either, because Japan is not a small island. It's actually quite a big island, which is interconnected between different regions. So I think this is how we wanted to start the discussion, to show that yes, Japan is a bit different. Yes, there is actually some constraints, and inertia is an issue in Japan, where it's not so much an issue today. But at the same time, there is solutions. And I think this was one of the important contributions we wanted to bring to the debate. Renewables can also actually contribute to maintain grid stability. So if grid stability is not so much the main issue today in Japan, so what is the main issue? I'm a bit having a provocative kind of question there. And I identified, in my view, three main topics, which, from my perspective, should be assessed in more detail also in the future. So the first one, I think, is really to promote a flexible use of resources in Japan. We need flexible resources to minimize the variability of wind and solar power. And as a matter of fact, maybe Japan is not interconnected, but Japan has a very strong flexibility asset in its system. It's the hydropower. Like Germany has very little share of hydro. In Japan, you have already a significant amount of hydro. So using hydro in a more flexible way could be actually something which helps to integrate wind and solar power. But not only hydro, conventional generation can also actually contribute to the flexibility that we need in our system. So, for example, coal can be activated flexibly, as we see typically in Europe. Now, we said there is no interconnection between Japan and the rest of the region. So there is some project, maybe in the long run, to have this Asian supergrid. But before even thinking so far away, another integration solution is just to integrate better the regions within each other. And in our study, we showed, for example, the benefit of integrating East and West Japan for the stability assessment. But more globally, when we think about the market integration, it's not even speaking about new grids, it's just having better operation rules between the region. This can help integrate higher share of renewables. And there is also the need to incentivize demand-side response. A demand-side response is a very low-cost flexibility resource. So I would say grids, I would say flexible generation, demand-side response, it's the three key flexibility options. And only after I would start to really think and speak about storage. Because we need to go step by step. So the least cost option should be incentivized first, and then maybe we may need indeed to assess the potential and the benefit of storage. So this would be my first important point. Utilize better the flexible resource that you have. Then the second one is the markets or the rules which govern the operation of our systems. And here, I think it is time to design a market which is fit for renewables. I think renewables have shown that they are fit for the market. The costs have gone down in most of parts of the world, but also in Japan, the cost of this technology is reducing. And now with this auctioning system that we implement, we will maybe see also a cost decrease. Further cost decrease in Japan. So renewables are fit for the market, but now the market needs to be fit for renewables. And in this regard, I think this is legitimate that we ask renewable to have more responsibilities in the system. Like in Europe, renewable are balancing responsible parties. They contribute to the balancing market. But at the same time, we should be sure that we design a market which will also be non-discriminatory to the different technologies. In Europe, we have requirements, pre-qualification in the balancing market, which allow renewable to actually contribute. But also, we have developed short-term markets, which are very important for integrating renewables, because the closer you move to real time, the more you can get use of the new forecast information, and the best you can just trade, balance your energy supply in a way that make, at the end, the integration challenge easier. So a market which is also fit for renewable, I think it's fundamental. And now there is a broad discussion in Japan about the design of the balancing market, maybe going to an intraday market which has shorter product time, like 15 minutes, for example, like in Germany. I think these are really important contributions to integrate renewables at lower cost. And the third component, I would say, has to do with integrated grid and resource planning. So the objective of a transformation is to minimize the costs of the overall system. In order to minimize the cost, we need to take a system perspective. And with the decrease of the generation costs, it is important sometimes to move renewables closer to the load demand. If you move them closer to the load, then you save actually grid costs. But it is also important to look at your best resource, how you can balance them. Typically, wind and solar, they make a good actually match. They have a different correlation pattern. So using them both is actually, from a system perspective, a very important driver to reduce costs. So in order to do this resource and grid planning, some state-of-the-art practice should be implemented. In my view, as the experience in Europe has shown, using, for example, curtailment, allowing a little piece of curtailment when you plan your system, 2 or 3%, allows you to save a lot of grid costs. So it should be integrated in the logic. Maybe not every kilowatt hour needs to be fed in the system. Let's say 98%, and the rest allows you to minimize grid costs. Another important practice is to better utilize your infrastructure. And here there is a lot of technology which exists, like dynamic line rating, for example, which allow you to use your grid at a higher level than the physics would, in a conservative way, say. So these are the 3 important topics: designing market, using better flexible resources, and have an integrated planning and resource management approach. These 3, if you take on top of that the 4th one, which is the one we assess today, so grid stability, are important contribution for the debate. On these 3, I just spoke, we didn't yet worked on this together with Renewable Energy Institute, but we plan to do it in the future, as I think this would be an important also contribution to these debates. So this was my contribution for today, and I'm very happy again to have done this work together with my colleagues here of Renewable Energy Institute, with the consultant, and I'm looking forward to have the discussion with you. Thank you very much.
Next, Professor Yo Yasuda, Project Professor, Graduate School of Electronics, Faculty of Economics, Kyoto University. Professor Yasuda, the floor is yours.
皆さんこんにちは。
Ladies and gentlemen, good afternoon. And my name is Yasuda from Kyoto University. First of all, well, thank you very much for inviting me as one of the panelists today with such a large turnout today. And I personally am not really engaged in the studies this time, but from time to time I was asked to really give my comment. And so the analysis by the third party perspective was really well conducted this year. And then I am also, again, the third party person to provide some inputs to their studies. And today, from the first half, you have been listening to all the presentations. What do you think? And compared to the usual Ray symposium, it seems like a very difficult presented inertial and MR and all these technical terms are so really many. And I think I was invited to speak here to make it easier for you to understand what's being presented. And so, quickly, I just prepared this kind of slides, and this is something I have just developed, and so I was really preparing the presentation material just immediately before the presentation, and I'm giving a very difficult time to the simultaneous interpreters, and apology from me. And I will be speaking at a slower rate, and then for the non-Japanese participants, I am going to give you the copies of the English version, and here. Myth and misunderstanding about the renewables, particularly in Japan. This is the very widespread myth and misunderstanding. And as you have more of the renewables, you will see more of the outages. I think you have heard of this. And particularly, we have some people from the media. And, I don't know exactly, but, more renewables will lead to, more outages. And then this is a sort of catchphrase. But this is, really, something from the last century. And you please don't talk about the new technology based upon the older knowledge. At the end of the day, actually, the blackouts in Hokkaido, and Professor Tsuji is going to talk about that. And the blackouts in Hokkaido was totally unrelated to renewables. And even without renewables, there is a likelihood of outages. And also, even if we have the larger sort of feed of renewables, in Europe, they do have really developed the measures and technology to avoid outages. And there should not be no outages, but rather, in terms of probability, what would be the percentage of the outages? And that should be the perspective we should really have. And more renewables lead to more outages. This is somewhat the knowledge from the Edo era, which is very, very more than 100 years ago. And then this is often said with respect to the Hokkaido. And if we have the distributed generations, could have prevented blackouts. Is this really true? I just wonder. And personally, I am we're learning all this electrical engineering, and I think this is too excessive in saying that. And then the too optimistic the statement vis-a-vis renewables should not be really used. And if we have the distributed generations, the grid stability might become worse. And it is true. And in terms of the sort of engineering and also the various theories, it is true. So we cannot be too optimistic. However, should we be pessimistic? No. As we have been listening to the presentations of various different parts of the world, there are many measures which have been established and proposed. And so in terms of probability of the outages, it is not going to be high. And as Mr. Günther said, even if they have more of the renewables, statistically, they are really reducing the incidence of the outages. And there is no direct relationship between the more renewables leading to the more outages. And so we should have more of the discussion based upon the quantitative data. And so there is a need for quantitative grid analysis. And if we are just really using imagination, and then we're talking about the likelihood of outages, that should not be the case. And so we should really be looking at the significance of the study conducted by Ray this time. Now, I'd like to share with you an interesting diagram, and this is from the Migrate in Europe, and they are spending quite a lot of money, and this is almost a quasi-national project in EU. And the researchers do know of this, but it's not translated into Japanese, and so I think not many people are aware of this. What this shows, the power electronics inverter and converter penetration on the horizontal axis in terms of the share of such penetration and the stability of the grid, and the blue line over here. And power electronics and the distributed sort of the generations of the renewable energy. And as we have more of them, the grid stability gets worse. And that cannot be helped. It is true. And according to the current technology, and if you are to really counter-argue, it's not really the case. And so we have to really understand this and introduce more of the renewal. And this is a transitional period. And because of the development technology and innovation, we will be able to really raise this. And we need to have more of innovative technology. And digital grid is often talked about here in Japan. And the next generation technology will emerge. And therefore, this time. So somewhere in between, in the middle stage, we have the most severe situation. And we would like to really promote the renewable energy, and those people should really recognize this. It's not that the introduction of renewable energy will just give you the rosy picture. No, we have to have the discussion based upon technology and the Migrate European project. If you could just search it on the website, you will be able to get the English information. So I hope you will take a look at that. Now, inertia was talked about in the earlier presentation. Is my time up already? My time is up? I understand that. So I cannot really speak too long. And inertia, and when you have the turbine rotors, and then this kind of the rotator will rotate, and then if the inertia is lost, it's going to be putting us in a serious situation. And Mr. Onishi is going to talk about the GE and other companies are really trying to come up with the measures to improve this, and that has been long discussed quite some time. And also Mr. Wakayama talked about if you have any incident in the grid, and then this is what we are going to see, and it might lead to the blackout because there is a certain threshold. But this is not really caused by the renewable, but in a big thermal power plant and a big transmission line, if they fail, and then this is what we will be seeing. And the intelligent control of the renewable energy, MRR, and also all the other types of the intelligent controls are put in place. Then the renewable energies do not do any bad to the grid, but they will be able to make contribution to the grid stability. And lastly, let me speak another 30 seconds. And IRENA has released this lately, and according to their report, and the Ministry of Environment has really uploaded the Japanese version on their website, and I did the translation of this English text. And this is the sort of the suggestion of the electric power system analysis, and this is a chart in view of the time resolution, and this time, and raise wishing Purchase, the report could be well positioned somewhere here, and by utilizing switch model in each seasons, and super system. What was the term? Power factory. Yes, yeah. Power factory was really used as a simulator because there are so many different ones, but in-depth analysis was conducted. And likewise, and this is also the IRENA report, and this is where the analysis was conducted. And digressing, and the Kyoto University is conducting the analysis over here. And in this way, various researchers and inclusive the electric power companies and independent researchers and research institutes are using different models to really conduct the calculation. And as you see more of them, and by having more people involved, would be able to provide the demonstration and verification of the new technology. Probably, it's not so active here in Japan at the scientific society and others. We have not seen much of it, but it's very active out there in Europe and others. And so we would like to carry on more of the in-depth discussion. And then this concludes my presentation. Thank you.
The next speaker is Mr. Hideyuki Onishi, Regional General Manager of North Asia of GE Renewable Energy. Yes, there it is. I am Onishi. I am with GE. Thank you for giving me this opportunity. Professor Yasuda has just spoke, and the reason why I am speaking after him, and I am going to regulate that time spent by Professor Yasuda. I will be the regulation power source, in a sense. I am given 5 to 10 minutes, so I want to focus on 3 points. First is about wind power. Already has the capacity to stabilize the grid. That's what I would like to briefly explain in the first place. And in what way, when we connect wind to the grid, how are we going to leverage grid stability capacity by using grid code? And thirdly, this research this time was conducted by a third-party institutions. Therefore, I would like to talk about the importance of transparency and sharing of research results such as this. I don't have enough time to explain in detail this page. First of all, wind farm has the capacity to stabilize the grid, just like thermal power plants. The output control, needless to say, and also ramp rate control, how many megawatts per minute can be controlled, and also frequency droop. When frequency changes, goes up and down, output can be changed in order to maintain frequency level. That capacity already exists, and also voltage control. When voltage changes, in this way, the voltage is controlled by wind power. And inertia is another feature. So large power plant event, in this study, 1.5 gigawatt, when there is a loss of generation, in order to avoid the collapse of the grid as a whole on a second-by-second basis, the grid stability is to be ensured. So generally, thermal power plant has a superior capability in this area. However, already in wind power area as well, these features can be supported. Already, these features are available at default wind turbines. However, in Japan, that kind of features are not at all utilized and leveraged in Japan. Now, let me give you some examples. the thermal power plant, the grid stability capacity, and also wind as well. Of course, there are areas in which wind is better or thermal power plants are better. So we have to understand which type of energy sources is capable of doing what. So simply put, the fast response is sometimes required in certain events. In such a case, wind is quite good rather than a thermal power plant. In some cases, wind is superior. In this case, 10/60 seconds, voltage comes down. In that case, the red shows the thermal power plant response, and black shows wind response. So for some functions, wind is not at all inferior. As I said earlier, inertia capability. So by one wind turbine, we conducted a test, and the frequency drops by 1. As a result, about 15% or so of rated output can be compensated for by that. So this is the result of this test. So as people have thought in the past, there are functions that can be supported by wind as well. Already in Quebec, Canada, and Ireland and Ontario, this has been required in the grid code. So in various countries going forward, this will be required in tandem with the introduction of wind and solar PV in the future. This is going to be a standard requirement in the future. So as I said, wind has an inherent capability. How are we going to transfer that capability onto the grid? How the grid can leverage that already existing wind functions. And in this case, grid code goes a long way. System operations rule, in other words, this is one example. Ireland and Denmark examples are shown here. Wind farm level control. So wind farm as a whole, and also the each individual turbine level. There are different requirements of which the details have to be omitted in the interest of time today. But in a sense, wind farms, to what extent wind farms will be made to be responsible for grid stability. So grid code is a rule to define the extent to which wind farms are required to play a role in grid stability. So I am going to give you 2 examples to illustrate the importance of this. So this is going to change and evolve as we speak. One example is Texas. The wind power is being introduced in a large way, 70 gigawatt in Texas, and TEPCO has a 65. Therefore, it is about the same, or maybe Texas is larger grid than TEPCO. 21 gigawatt wind farm is being operated according to 2017 statistics, and 50% maximum wind can be supported. And here, they have a very severe, stringent grid code. How stringent is that? The already established, installed, and operating turbines, farms, they are subject to new rules as well. By so doing, introduction increases. So this is a very stringent grid code. That is a Texas example. Because of this stringency, the uptake of renewables is increasing, and regulation reserve maybe will increase according to some people. However, 7 gigawatt was introduced in 2011 through 2016. During this period, regulation reserve requirement actually dropped. That means grid code is constantly revised to make it more stringent, and the rules are modified in accordance with that. And other thermal power plants and also wind side operation are also updated. By so doing, total cost can be reduced. So this is indicative or in this example. And also another example often cited is Ireland, 6.8 gigawatt. It's like Hokkaido. Hokkaido has 8 gigawatt, so about the same. And in that, 3.8 giga is wind. So constantly, 25% or so power is provided by wind power. And the 70% is the maximum penetration of wind. So what is interesting in the case of Ireland, they use a NSSP, System Non-Synchronous Penetration Index. So how much PV or how much wind can be introduced so that tolerant range of the grid is increased, and based on that, system innovation and technology innovation is pursued. So technology innovation is pursued by using this index. And as is often said, Ireland is maybe interconnected to European grids. That's why this is possible, according to some people. However, there have been 2 incidents. In February 2010, they have a pumped storage generation to provide grid stability. However, pumped storage were dysfunctional, and therefore, these were absent from the grid. However, the accidents were avoided. And the other incident was even more severe. The grid was disconnected and cut off for 5 months from external, so they lost external regulation capacity. So this is a completely island situation. Even in that case, 17% of electricity demand was fulfilled. So Ireland was able to overcome such problems. Now, this time, we have a German-based consultant company involved in this research project, which is very significant. And this should not be one-off project. Maybe such a project has to continue on a constant basis going forward. So if you want to know whether you should listen to my presentation, but that is like asking a fish shop to buy fish. So we are offering a consultancy service, but already we have a lot of know-how and expertise. So there are many consultant companies. Therefore, maybe we should exchange ideas and views among peers so that we can brush up our idea and knowledge. So I have to conclude. So this is the message that I want to convey to you. Wind power or wind turbines, you shouldn't spoil wind turbines. You have to impose very stringent requirements on turbines. And in tandem with that, we are able to promote technology innovation and also system operation upgrades. So wind farm is not a special existence. Rather, wind farm can play a role in stabilizing the grid. So a stringent and harsh grid code should be used to increase requirements onto turbines. Thank you.
Next, from Yokohama National University, an associate professor, faculty of engineering, Professor Takao Tsuji is going to be the next speaker. Tsuji from Yokohama National University. First of all, and as well Professor Yasuda said, Well, as for this particular project, I was not directly involved, and from time to time, I was really be a part of it from time to time, and so that is the position I find myself in, and grid stability is the major theme. And then when there is the sort of loss of generation and frequency drop were included in the sort of the analysis, and that was the scope of the study. And I'm sure you are very aware of this, the blackout in Hokkaido recently, and that was sort of the similar incident. And so today, to recap the overview of that particular incident, and also we would like to really introduce this particular incident to the non-Japanese the researchers who have worked with the particular study and international symposium, and I prepared my presentation material in English, and probably it may be a little difficult for you to understand, but please bear with me. Now, the blackout in Hokkaido, which took place at late night on September 6th this year, and from September, they had 4 meetings by the financial investigation committee, and I am one of the members. And then last week we have concluded the investigation activities, and then the final report is to be compiled. And so, based upon the discussion and information I have obtained, I'd like to share with you some of the experience here. Now, 3 a.m. on 9 September 6th, and then there was a very small demand, and then there were 8 gigawatt is the sort of the total capacity, and 3 gigawatt also was the demand at that point in time, and very low demand, and then the earthquake took place. And Tomato Atsuma plants, and then there were 3 thermal generators, and also 3 of them were really stopped after some time with a time gap, and also 4 transmission lines were stopped. And so, one of the grid pollution was isolated, and then all these have the major loss of the supply capability was experienced, and then the frequency significant frequency drop was also experienced. And this shows the Hokkaido electric power companies the control area, and the Tomato Atsuma power plant is very close to the epicenter, was shown in the blue, and then out of the 2 stopped, and then because of mechanical failures and more than 10 minutes or so, while the remaining our plant was also stopped. And then in the red-colored box on eastern area, and also the loop area where you have this the central part. And then because of the 4 transmission lines were disconnected, and then they were totally separated. And then those of the hydro power power plants, which were included in this red, also stopped its operation. And just for your reference, and this is the sort of overview of the supply capability or supply power at that point in time, and to Atsuma and coal-fired, and in terms of the economic rationale, it is efficient, and then the sort of the supply sort of the capacity was concentrated in this, and then because of this concentration, the power sort of generation really was lost, and then that has caused this significant incident, and the major loss of generation, and according to simulation shown earlier, and the frequency has a significant drop, and according to simulation earlier, and around 49 hertz was considered to be the threshold, and if it goes below, then load shedding would be conducted, and that was a sort of the overview. But actually, it has gone down all the way to 46 hertz or so, and then most of the people were really shedded, and then the load shedding is shown here, and a quite large number of the load shedding was conducted, and because of the smaller scale in Hokkaido, but they do have the interconnection between Tohoku and Hokkaido, and then by utilizing it, emergency power supply from Tohoku was conducted up to its full capacity. But because of that, but even then, and thanks to such a control, well, spontaneously, there was a recovery of frequency. And I'm sorry, I'm just jumping one from to another. And the blue, and then you had the recovery of frequency at one point in time. But more than 10 minutes later, the remaining the power plant was shut down. And there was a shortage of the supply power, and all the load shedding was exhausted, and there was no way to really prevent the outage, and that has resulted in a major blackout. And towards the future, and we have to really investigate and analyze the cause of this blackout and what kind of countermeasures can we really consider. And that has been really discussed at the investigation committee. And renewable energy is going to be increased in its supply. But just Tomari a power plant to really restart its operation. And then, if there is a sort of the breakdown of the Tomari, there's going to be a significant impact. And assuming that the countermeasures need to be considered, and that has been considered. And for one measure, and UFR under frequency relay and the mechanism needs to have more additional functionalities and features. And on the left-hand side, the conventional UFR being used by the Hokkaido, and if it is go below the threshold, and it was spend some time, and if the frequency cannot be recovered, then the load shedding will be done. But as shown on the right-hand side, when the frequency starts to decline, and as shown in the earlier presentation, and the rate of the frequency change, and if there is a dramatic change, and then we can really predict that it will drop to a significant degree. And so in order to really ensure on a higher stable operation to be recovered, we are to really do the load shedding early on. And so and 3 plants in operation in Tomari, and if there is the stoppage of all of them, and then that will eventually lead to a major blackout. But by using this the DFDT relays, we will be able to prevent a significant incident from happening, and that is the result of the analysis done. Therefore, in this way, and in today's presentation, 1.5 gigawatt. And loss of generation was being assumed, and that was the basis of the study. But if we are to really assume more severe and excessive the conditions, and to weather through this particular incident to really avoid the blackout, we may have to resort to the load shedding and then come up with the countermeasures, and we may be forced to be in such a situation. And for each of the system, and as we see more of the renewable energy being used, and what kind of improvement should we have to the functionalities. And so we have to really look into such countermeasures where we are really pushed to that very threshold and to the very limit. As has been discussed, if we have more of the in-feed for the renewable energy, and inertia is going to be lowered, and then the rate of the frequency change at the time of the incident will be fluctuating a lot. And then the output of the renewable energy, depending on the time of the day, inertia will be quite different from a given time. And then depending on the time of the day, probably we will see the different rate of change of frequency. And also with the new technology of the inertia control technology, we may be able to see the different types of behaviors as we introduce more of the virtual the inertia technology. And so in order to really make the system more robust and flexible, and to really prevent the blackout to the extent possible, we may be able to really consider all these different countermeasures in a comprehensive manner. And just for your reference, in the middle of this the new protection system, and to detect the change of the frequency change, and then not just to really shed the loads, but decentralized stabilizing system, which is more of the information system to utilize. And then if there is a severe incident, we may be able to really do the load shedding, and that should be included in the scope of the analysis. And with the development evolution of ICT, we may be able to think about the introduction of more of the advanced information technology. This concludes my presentation. Thank you.
So from this point onward, I would like to invite 3 speakers from the first part of the program to start a panel discussion. The moderator is Ms. Mika Obayashi, Director of Renewable Energy Institute. Thank you very much for the kind introduction, Mr. Ichimura. And following the first part of the program, thank you very much for listening to presentation very enthusiastically. So Professor Yasuda talked about Ray. Usually, this symposium is quite different from the usual Ray symposium. We are hearing a lot of technical terms today, but on a day-to-day basis, we are having such a technical discussion. Without technical discussion, we can't make progress. As was mentioned by the speakers already, in the beginning, I had an opportunity to speak, but I was quite nervous at that time in the beginning because Mr. Shaibuna's presentation stopped or finished earlier than I expected. Therefore, I was quite nervous because I was called up quite suddenly. So I want to show you that last part of my presentation materials. So once again, what we wanted to say through this research project, and also in what way are we going to utilize those recommendations to policymakers. And of course, Peter mentioned about that already briefly. But let me give you some more explanation.
ちょっと英語と日本語
So we have both Japanese and English, and I'd like to share the Japanese slide. And in the on the summary and as the highlights for this page was included, and in the Japanese power system, and the Japanese power system can accommodate a larger proportion of wind and solar energy that is currently provided for in government's 2030 targets, while still maintaining grid stability. And as I have said, 33% of the renewable energy can be easily being integrated. And as a result, we will be able to really look at the higher renewable share of 40% in 2030. And so, the 2% share of the VRES. And then Wakayama-san has touched upon this already. And also, there already exists a number of technical measures to improve grid stability in situation where a proportion of variable renewables could place a strain on grid operation. It is indeed true that there is going to be a higher load, but even then, the technological the measures are still in existence to really improve and ensure the grid stability. Mr. Onishi, wind power generation already, technical solutions are available, but they are not really being used in Japan. And that was the sort of the issue pointed out earlier by Mr. Onishi. And FFR services, and also the curtailment of the output. And there are various measures, and whilst exhorting to the measures, as Mr. Wakayama mentioned, up to 60% in Eastern Japan and around 70% in Western Japan. And the instantaneous VRES penetration levels could be achieved. And the instantaneous, and in Kyushu already 90%, in Shikoku, and many VRES has been introduced. And so this kind of phenomena, and they are being localized as of today, but by 2030 or even in the latter 2020s, this will become known here in Japan, and that's our thinking, and our integrated grid and resource planning can help mitigate the impact of wind and solar PV deployment on inter-regional and inter-regional load flows. And Dimitri has also introduced this, and not to think about the grid and resource separately, but policy-wise, we should integrate them together and do that planning. And also, furthermore, non-discriminatory market regulations and enhanced transparency and improved the transparency and state-of-the-art operational and planning practices facilitate the integration of the higher proportion of variable renewables. And Peter has also mentioned the recommendations to policymakers and to really implement non-discriminative market regulations, also to really improve the transparency of data. And it's not just to really allow the third party to do the grid analysis, but all the market participants can share the same information and to make a decision as to the participation, and also they will be able to really do the investment planning. And that is the proposed by us, and then by the third of the promotion of the third party third of the study, and also they really have to really do the renewables should be incorporated into ancillary services provision. And as Mr. Oni said, there are so many services available, but they are not much used here in Japan. And by utilizing them to the full degree, and then we will be able to ensure the grid stability and introduce more of the renewable energies. And BCB on the regulation as to the energy providers, they to modify the service requirements, and Onishi-san has touched upon that, and also Peter and I have the discussion. And all these renewable energy providers, energy providers are technology-oriented people, and they are capable of really satisfying all these requirements, and we are very confident on that. And so predicting the grid service requirements and then try to accommodate that. It's not just a sort of energy supply services, but other ancillary services should be taken into consideration. And so that is a sort of the policy recommendations we have come up with.
でこういった提言をさせ
And based upon these recommendations, and firstly, and the very first speaker, Mr. Günther Scheibner, I would like to really ask a question. And our policy recommendations and themselves are we really 60% in Germany target. We are just targeting at half of it or so. But while going through the discussions and also by taking account of the Japan's state of affairs, can you please give us some comments from your perspective?
From my perspective, everything can be possible. And at least as it is shown in Germany, to reach a limit of integration of renewable energy, we cannot tell you a limit, because the different situations have different measures, and if you consider that the whole system has to be changed, not only one part, not only the generation, but also the transportation, the transport, the distribution of the grid, of the energy through the grid. And also, at least we can tell you that all the different functions, depending on weather forecast, everything depends on weather forecast. And we cannot maintain something on the grid without taking into account the infeed from renewable energies, the infeed from wind, and the infeed from PV. And so you have to discuss all the pieces together. You have to put the puzzle together and to figure out a new system which also takes into account a new market structure. You have to decide what has happened on the market, how the integration of renewable energies to the wholesale market. It's one piece. The second piece is the integration of the renewable energies, as we heard today, to the balancing market. It will be one of the next steps also in Germany. We are on the way. We are on the beginning of the discussion about the integration of renewable energies to the balancing market.
ありがとうございます。
Thank you so much. So market utilization, that perspective. Here in Japan, system reform has been launched little by little. The new market is being established. Professor Tsuji, sorry to pinpoint you, so the discussions on new market and integration of renewables, would you like to make a comment, please? Thank you. Demand, supply, and the adjustment committee is where I'm a member of. So renewable energy is on the increase, and sometimes you feel that we could do everything, and we knew the system, but in this system, economic perspective of great importance to that end, market must be utilized. So optimum, the overall optimumability is important. And then there is a transition to the market. In Japan, 2021, there's market for the flexibility, and 2024 capacity market will start. Many things will move into markets. So again, the METI and OCTO have been addressing these issues. There are several important issues. For instance, system as a whole, that consistency in the system as a whole, that is of great importance. Not just in the flexibility market, but how best we can improve the markets, the FIT special measures, based on 2 days before the forecast regarding the output of renewables. That's basically there's a day-ahead market and intraday market. Those markets, they are not actually used to adjust the FIT, so that's distorted. We can enhance that as we now have tried to create this flexibility market imbalance prices. So to have more stringent rules so that there will be less imbalance. And the flexibility, you should also have the good incentive and try to have better the resources available. Those sound similar, but these are two different things. We need to address them more appropriately. As was mentioned before, the flexibility the resources with more experience that required flexibility may decrease. The balancing group expansion and intraday market, more flexible operation, there will be many factors involved. By accumulating experiences, that's so important. At OCTO, regarding the required flexibility amount based on the past data, the required volume decreases with the standard deviation up to the 3 sigma. You should ensure that. People tend to be on the conservative perspective aspect, but do we really need to be that conservative? And as Mr. Onishi said, regarding the flexibility resources, the renewable energy can make a contribution to them. Then overall, it can be more reasonable to reduce cost. The consistency among different systems should be looked at. That's all. Thank you.
Thank you. But, well, having listened to what you speak, well, it sounds quite true. But in building the markets, there could be a lot of inconveniences, and we have to really overcome and correct each of the problems one by one. I think that's what we are now doing, and it might really take some time. And this is the impression I have. And Professor Yasuda, do you have any comment on this particular point? So building up the market and how. And today, well, you have really explained a lot of things about the renewable energy and variable renewable energy, how that could be integrated into the market effectively. And you have not really touched upon that particular point in your presentation. I was certainly appointed, and there was no sort of the storyline of this was symposium, panel discussions. I'm just lost what to say, but inclusive of my personal observation, I like to really share my views. Now, the power market, and those of you who are interested in the electric power market, and I'm sure there are quite a large number of experts here, and then specialists. I think they are really watching the market and also interested. But in your day-to-day conversation, do you really talk about the electric power market with your wife, with your children? Well, if it is the stock price, even those who are not really trading stock, they will be talking about whether the stock price is going up or going down. The stock compared to the stock market, and whether we are really talking about that in our daily conversation, even though they are not really involved in that, there is not much of the discussion by many of the Japanese people still, and it's quite far or remote from them, and even because they are not so much interested in the less transparency, and many citizens, inclusive of the media, if they are more interested, and then they will be able to be aware of some of the shortcomings and deficiencies. And so if we have more of the citizens' eyes, then the market will become more healthy. We can really criticize the market mechanism is not functioning well, and then there is going to be more of the inequalities going forward. But it is because the market is not really well designed, and then if they really think that they should be avoid using the market, and more people are really getting away of the market, then that would not do good. And so even if they are not really the market participants, then, I don't know if in Europe or Germany, people would really talk about the electric power market in a daily conversation. But if that could be really achieved, and then we will be able to have more active market. And then transparency is one of the keywords often used in the discussion. It's not something which would be given by the God or heaven, but each individual citizen needs to be interested, and that would really enhance a healthier market. And the discussion on a power market is being held here, and I think this is very significant. Probably, this is not the answer you have expected. It's slightly different from what I expected. And so the discussion vis-a-vis the market, and we would like to have the more in-depth discussion on market.
Earlier, we have been having discussions today among our recommendations, as we say, and Professor Yasuda is always saying this, but earlier Mr. Onishi said renewable energies already have a ancillary service capability. So such capability utilized in Europe, and those functions are integrated into market. Now, among our recommendations, we would like to give such function to renewable energies. So that is one of our recommendations. So I was expecting you to make a comment on that aspect. Then let me try to respond. Today, Peter, I think, Günther-san, I read, can I have the presentation materials of Günther? His presentation materials toward the end, there was a very important example of Germany. Maybe you have already noticed, page 18. Page 18. Can I have it? This graph. Maybe this is understandable for European people, but maybe this is not so easy to understand for Japanese people. So allow me to explain this in Japanese once again. Now, in Japan, renewable energy, if it is introduced more and more, backup power source would be necessary. That means thermal power plant have to be more active and CO2 emissions will increase. This is groundless. But as you can see, the green line shows a share of renewable energy integration, and the regulation capability requirement is actually declining year after year. It is very interesting. If you go to a classical way of thinking, if you increase the share of renewable energies, regulation capability regulation has to go up. However, this is a German paradox. Why is it possible? Of course, there is a technical issue, but there is a design of a market. Market was very well designed, regulation power market, and also the day-ahead market, and so forth. Not only technology aspect, the system design has to be very good. This is a very good example. So I think Japan should take a lesson from this. So in addition to that, renewable energy has a capability of providing regulation function, and this has been already discussed since 10 to 15 years ago in Europe and in US, so we have to make a catch-up in Japan as well. We shouldn't say, we can't do this, we can't do this. Rather, we should come up with ideas, better ideas to enable a renewable energy integration.
コメントというかあり
About the German paradox, any comment, Peter or Günther?
It is called the German paradoxon, yes. But not only, at least on this graph, the renewable energies are not included into the control power. It is mainly the reduction of the used control power mainly comes from the cooperation of the TSO. The interconnected TSO cooperate quite well together, organized a shared market, and used the possibilities of the different TSO systems to reduce the usage of the control power. So it comes up like a paradoxon, but it was developed by the TSO cooperation in between. And so we could reduce tremendously the use of the control power. But if we integrate also the renewable energies, in Germany the law has stopped the integration up to now of renewable energies into the control power usage and in the flexibility markets. But in the future, it will be changed. We are on the way also to change it and to integrate them as a normal producer into all market shares, also for control power market and, as it is currently, also to the wholesale market.
安田先生よろしいですか
Thank you. Well then. And I'd like to really ask questions to Mr. Onishi. And you have cited several examples and talking about the grid rule. And then by establishing grid rules and then to be reflected on the use of the more of the renewable energies. And Professor Tsuji also talked about within the market and then renewable energy grid rules, how that could be established. And if you could elaborate more as to the grid rules so that everybody will have the better understanding. Can you please elaborate more?
Where can I start? The renewable energies. How are we going to integrate renewable energies in energy mix? The fuel, if it is free of charge, if it is to integrate it into the energy mix because energy is free of charge. But we have to take risk. We have to introduce new technologies to do that. Now, one of the technology parameter is a grid code. Grid code, based on grid code, the integration rule is defined. And depending on the market change, a demand change, we can revise the grid code. In the case of Texas, in the US, very frequently, maybe every year or every 2 years, the grid code is revised, and they are moving in a better direction by doing so. So I think we can learn a lesson from this practice. So at the beginning, maybe the code is imperfect, but gradually it can be updated and revised to make it more perfect. So that's what we have to do. It's evolutionary. Professor Yasuda said there is a need for transparency and clarity. Listening to the presentations today, there is another point, that is a fairness. Fairness is also important and needed. So renewable energy, we can do anything for renewable energy. That should not be tolerated. Within the power mix, what kind of roles to be played by renewable energies, and also responsibility and rights given to renewable energies as well. And we have to come up with the best mix of such functions depending on type of energy sources. And we have to make a fair burden sharing in Japan. So I think this is a part of very interesting social experience we are engaged in. Thank you.
Dimitri?
Add one word regarding the responsibilities, which needs to be indeed fair between technologies, and maybe refer to this graph we saw before. I also think this is one of the most fundamental graphs of showing how good market design, even though market may be not a discussion everybody has every day, but how good regulation can improve innovation also. Because of responsibilities given to renewables, renewables were forced to go away from this just produce and forget. They had to also contribute to the responsibility of the system. Then it triggered innovation in forecasting, better forecasting. Then they came into being active market player through aggregation. It opened a new business model to be more balanced. So good regulation and responsibilities leads to innovation, and at the end of the day, reduce basically the cost of the integration. So I also think fair responsibilities, and in Japan now you have also a lot of renewable in the system. It is, in my view, normal that renewables take responsibilities, but it is also normal that we give them then access to different markets to value their contribution to the system integration.
Thank you so much. Then we would like to entertain some questions from the floor, please. And then to the members of the panel, we would like to ask them to give us their concluding remarks. Will there be any questions from the floor? If you have, please raise your hand. One person, several persons.
ではどうぞ。
May I please identify yourself? I am environmental planner. Suzuki is my name. Thank you very much. Since some time ago, I have been listening carefully to your remarks, but I couldn't come up with a word. The biomass, the wood-based biomass generation, power generation in Japan, 70%. Japan is covered with forests. 70% of Japanese land is covered by woods. Therefore, wood biomass power generation can be even more vigorously pursued. By so doing, it can be positioned as an important renewable energy source in Japan. So what is your view regarding the use of wood biomass? Thank you very much. We talked about variable renewable energy mainly, so that is why bioenergy was not taken up. That is one question. And also another person over here, Aikawa-san. Iwasaki, I am with Tokai University. The Tsuji-san, Professor Tsuji's question. Hokkaido power blackout incident. In this connection, in the government investigation committee, the Hokkaido EPCO responded to this incident very, very successfully. That is the conclusion of the government investigation committee. However, Professor Tsuji's explanation, for instance, centralized forecasting could be one option, and also frequency or load shedding timing can be adjusted. So there are technical issues that investigation committee discussed. In the case of Japan, in particular, in that kind of situation, power plant itself was is facing a trouble because of earthquake, and also hydropower also was affected as well. However, on the other hand, renewables were functioning well, according to some people, if there is an intention to use it. However, unfortunately, under the Japanese rule, there was a prevention requirement of the isolated operation of renewables. Therefore, in the time of incident like this, renewable energy was not utilized, and after some time, renewable energy come back on stream. So all in all, that is my interpretation. All in all, system control, in what way blackout could have been avoided with system management? And how can I say, even if such an contingency occurs, I think renewable energy could have played a better role. So we have just received 2 different types of questions. First of all, wood-based biomass utilization, maybe discussion from German side, and also maybe Onishi-san can make a comment.
I'm happy to answer on the biomass. From a German perspective, biomass is not a main resource that we have because of land restriction. There is actually not a lot of biomass resource available. And also because of sustainability criteria, this is not seen as the most important renewable resource. And the final point is that the cost of biomass for producing electricity is much higher than the cost for wind and solar power. Now, in principle, biomass should have an important role to play when it comes to flexibility, because biomass power plants can be dispatched on demand. So if we have and want biomass in our system, we should use them flexibly. Now in Germany, they are not used flexibly. They run most of the time flat. This is an example of a bad, actually, incentive design. We may have to think about changing it. But globally, biomass will only keep a low role in our system in Germany because of the 3 reasons I mentioned first.
Maybe just one comment on the biomass. You say it's running flat, yes. But on the other hand, it's also participating in the control power markets. So it offers flexibility. I think almost every biomass power plant we have is pre-qualified for the control power market. So maybe that's a plus also.
はい、
At GE, we do have the mixed furnishing, the gas turbine, and so we can incinerate the biomass in the turbine. I think that's why I have been asked to address this. In Japan, what's the significance of doing biomass in Japan? Because 70% is covered by forest. We have a lot of trees, but most of the lumber, we actually depend on import. And the forestry, the roads have not been improved. So using this biomass, this mechanism, how best we can change the society from that perspective. While the per unit generation cost is high, but it's actually returned to each region, not just looking at the generation unit cost, but if it's, for instance, if it's 30 yen biomass, and the 1/3 or that, but half of them, more than half of them, as the lumber prices, if they can be returned to each locality, then there is significance. So it's different from PV or wind. So I think biomass has a role to play. It's an important power source. Having said that, if you look at the current system, if it's high, it's highly efficient. So the big power plants have been made, and partly because of that, most of the fuel is dependent on imports. So you can see the distortion that we have here. So when one creates many systems, you have to pay attention to the actual objectives, goals. What are the positive factors you need to make good coordination? I think that's a good example of that.
Well, from myself, and I am not a biomass expert, but from the grid control our perspective, and Dimitri-san and Peter talked about the flexibility, and then flexibility. And there is a sort of capability to really adjust or balance, and the wind generation and the PV, and then if you have more of them, there is no really base load, and then you need to have the capacity to adjust or balance, and then that flexibility should be required. Otherwise, all these who cannot really provide that needs to go out of the market, and then by having this kind of capacity or the flexibility, then you will be able to have the higher utilization rate, and then whether it is gas or others, the Denmark and others are doing, they are really selling the boiled water or hot water, and I think it's just about the half and half. Unfortunately, we have the fit electricity is available, but no fit heat, and all this heat is just abandoned, and all of them. And so, if we have this kind of system, then eventually, probably 20 years, 30 years, and 40 years down the road, biomass could be sustainable or not, it could be very challenging. Therefore, so by selling the hot water, meaning the cogeneration, inclusive of the local heating system, and that kind of comprehensive energy system should be really established. And so, in terms of the flexibility in electric power, and biomass can really make a contribution. That's my view. Thank you.
あるかなと思うんですけど、私
And for my part, we have Aikawa, who is a senior researcher. He is specialized in bioenergy. So maybe Aikawa-san can make a comment. Thank you for the introduction. Sorry, I am covering biomass. I am with Ray. With regard to woody biomass, the question was raised, and the panelists gave answers, and I totally agree. But unlike Germany, in the case of Japan, as a resource, the potential of biomass still remains. That is why I think we can accelerate the utilization of biomass. As was mentioned earlier, from the viewpoint of flexibility, from that point of view, almost all the power sources supported by FIT is only fit for power, not for heat. Another important aspect is heat, and heat is not supported through FIT, feed-in tariff. Therefore, we have to have a better design of the system so that resources can play a role of flexibility capacity. So our research institute, in September, we visited Germany, and therefore we had a comparison column at the homepage. So please read our column in our website. So electricity, only electricity, that means heat is completely discarded. What a waste.
質問いただきました。
Next question about blackout in Hokkaido. How could it have been prevented? So, Professor Yasuda, just a question for clarification. Distributed power generation, that doesn't help the outages. I understand that, but distributed power source would have made a difference. I think there's a kind of a mixed up in the discussion. Professor Yasuda, would you like to address this issue? Thank you. Again, I am not prepared, but this is just my personal view. You might have a different opinion, but personally, that blackout, never letting the blackout happen, that kind of line of thinking is not really the reasonable. I said probabilistic approach, because risk management is based on probability. It's not 0 or 1. What are the chances of that happening? In most of the countries, in advanced countries, once in 10 years, blackout, that kind of a big-scale blackout is looked at. There's a possibility, and then design the system. Because if you try to go higher, the cost becomes so exorbitant. So this is a trade-off with cost. So what are the issues? you can't just say, oh, it shouldn't make it happen. That shall never happen. But you have to start with the low-cost measures and address this. You can't be complacent. But should it happen once in 10 years, make sure that nobody will lose their lives so that health and property will not be affected. And in which way that you can do it more expeditiously, less expensively, that kind of a quantified discussion would be best, in my opinion. So that the distribution of parcels, again, you look at cost. In some cases, it's good. In some cases, even if you do it, sometimes it's so costly. Professor Tsuji.
Yes, well, this distribution, and I just like to really add one more comment. And this time, as I said, three the power units were stopped in one single power plant, and there was this the concentration, and then large supply capacity was gone, and also there were 4 transmission lines. It's just by coincidence because of the shaking of the earthquake. Japan line was shaken, and then there was a short circuit at the same time, and because of these incidents, and in the eastern part of the Hokkaido, and then hydropower power plants also have been stopped, and then that was kind of this the duplication of the causes, and the equivalent the hydropower plant, if they were not really be stopped, and then this kind of the major blackout could have been avoided, and this the centralization, the concentration, and the power plants in one single source has really caused this incident. And then this is not the right way of describing the phenomena. And as Mr. Yasuda, or Professor Yasuda said, reliability and cost and the balance between them. In view of that, of course, we have to look at some economic rationale, and then we are to really generate a more power in a more cost-competitive power sources, and that was the sort of direction of the findings of the investigation committee. And as you have really asked earlier, and back to your question, and distributed the power generation, and the incident took place and all the way to the blackout, and we're just focusing on that. And major frequency dropped down to 47 hertz, and that is what is believed to be the frequency drop. And then wind power generation were lost and then gone out. And then there was so much distributed power generation sources, and they were surviving, but on a high level. And all of a sudden we lost all these the wind generation loss. But it's not we should think ill of the wind power generation, but it is being positioned as that they could be really disconnected from the grid in such a cases. And as has been discussed earlier, FLT requirements needs to be reviewed, and that is the direction we are now pursuing based upon experience. Frequency goes down to a certain degree, and we will not really make it easy for the system to really stop operation. And then if there is a sort of demand and requirement from the wind power generation, we will be able to accommodate the request. And also to really inertia control might be applied to really prevent the frequency drop. In case of Hokkaido, the grid scale is smaller and the frequency goes, and then until reaching the frequency nadir, it will be just several seconds, and also it will go back to or recover to the earlier point in a matter of several seconds. And so in 10 seconds or so, we will be able to really give the recovery or achieve the recovery of frequency in case of the Hokkaido scale. And so just on a high level, this could be really possible. And so we should be proactive in introducing such technology. And whilst I was compiling an interim report, I really made the comments at the committee meetings, and because there is still vagueness with respect to the technology, and that was what we have discussed. And now, as for the recovery, to make use of the distributed power, and for that, in terms of the truth, the major power plant were not really started up, and and it took about 45 hours to recover all these the users' demand. And then the wind power generation also put back the system. And so we ought to make use of the distributed power generation and to really maintain the local power generation to the extent possible. And that kind of methods should be really pursued. And personally, the important key point would be, Japan really has natural disasters such as the earthquake to really damage to the major infrastructure, and really to really expand local the power source step by step. And vis-a-vis the failures of infrastructure, how effectively we will be able to address that, and we have to refine the technology and others. Otherwise, if we have this kind of major natural disaster such as earthquake, it will be the trigger of the major incident. And so we should be thinking about the introduction of such technology. Thank you.
One aspect. In Germany, we didn't have a blackout. I started my work life in '77, and up to now, I hadn't a blackout in our system. And but currently, we are thinking about how to restart after blackout a system with a high share of PV and a high share of volatile wind. It is a real challenge. Currently, we can say we can restart the system only during the nighttime and without wind, because the PV mostly is on the rooftop installed PV, together with the consumption of the houses where they are installed. Nobody knows, is it an in-feed, is it a generator, or is it a consumer in case of restarting a system. But in case of restarting a system, you have to have a clear position, consumption or generation, and not consumption or maybe generation, nobody knows. Then you can't restart a system. And we have to investigate currently how to organize a combination of different renewable energy sources, batteries, and maybe gas turbines, to have a small cell for restarting a system under a high share of renewable energies.
Thank
you, dear Dr. Wakayama. Well, Hokkaido was mentioned in a study about the interregional tie lines. Utilization of those interconnectors was mentioned, and Hokkaido and Honshu, the tie line further enhancement is being discussed. Dr. Wakayama, you talked about Kyushu and PV curtailment started, and as for the wind power generation, curtailment is being discussed. So from that perspective, blackout, the utilization of the tie line between Hokkaido and Honshu, and also about the Kyushu. What is your comment? Thank you. As for Kyushu and also for Hokkaido, DC and AC, there are differences, but they are both located at the edge of an island in terms of the demand area. So should there be an incident, accident, by that particular region, they have to balance and they have to ensure stability. So they have common difficulties of addressing the same challenge. Against the backdrop, because of the large-scale incident, how should we address these challenges? To think about solutions, of course, it involves cost, enhancement of the grids, and also connecting with other regions. Again, what are the costs? What are the benefits? Once again, you need to do that cost-benefit analysis, and one needs to address those possibilities as well. So cost-benefit analysis is one. With new tie lines, the enhancement of those new tie lines, it's not just for the grid stability. There are other benefits, and looking at all sorts of benefits and cost. So you shouldn't be confined in conventional ways of thinking. There might be some new ideas coming. Thank you.
Thank you. We were hoping to take was a little more questions, but we are now coming to the close of the panel discussion, and also wood-based biomass, and also Hokkaido blackout, and these are very the serious and deep issues, and probably we were not able to take the next question from the audience, but this time we have concluded the study, and in line with that, there are several policy recommendations to make use of interconnection, inter-regional connection, and also to really have the inherent functions of the renewable energy should be exploited in the market, and also to really not to design the discriminatory market mechanism, and also the questions were given to the Hokkaido blackout, and as we are really going to build more of the new power markets, I think they are really being insightful. And lastly, I would like to ask each individual panelist to give his or her comment in establishing this new power market. What would be the role of the renewable energy? How that could be integrated? And then, if you could really give us two suggestions in the order, and starting from Wakayama-san, can you really start? And from myself, related to the study we have just introduced. And lastly, I'd like to make one final comment. And this time, according to our study and the demand simulation and the grid model analysis, and if we have the spontaneous rise in renewable energy in field, what kind of countermeasures should be taken? And that's what we have really investigated. And according to analysis, and 30% of the renewable energy and 22% of the VRE. And if it goes above the government long-term target, and then there is going to be the need for more of the flexibility and others. And so that is the sort of the importance, and then that is the sort of the major message we have contained. And now back to the sort of domestic discussion and the level of the long-term energy demand forecast. And that would be the sort of the kind of the benchmarked the level. But what we have proposed, this kind of this stage will come later, and then long beyond the time horizon. But we were aiming at the 2030, and we are to really go faster, the introduction or the higher introduction of the renewable energy compared to what is set in the long-term energy outlook. And also we would like to really conduct the analysis and to really come up with the grid stability countermeasures, as well as to really get ready for the new market scheme design. And so the target values, in view of the higher values, and we have to really make a steady preparation, and that is important. And the role of the real energy would not be just to really curtail, but to really provide various flexibility functions, and how that could be implemented will be the critical point. Thank you.
Peter?
Okay. I'd try to wrap this up a little bit from my point of view. When you talk about renewable integration, you can maybe split it into three stages. You start from scratch, from zero, and up to a certain point, you don't care really much about renewables. You have them, you ramp them up, but they are not really affecting your system operation or markets or whatever. Then there comes the next step, where renewables get a little bit more noticeable. And I think that's where you are in Japan right now. And I think you should now really use this transition phase to prepare for the future, to think of new concepts, solution on all kind of levels, whether it's system stability, market integration, adequacy, you name it. You really have to look around on the one hand side, okay, what's happening outside of Japan? On the other hand, developing solutions which are really targeted for the Japan system, because it's special, has 3 synchronous areas and a couple of other specialities. So you can't just copy everything from somebody else, invent your own solution. And then finally, you can make the transition to a new phase where everything is dominated by renewables. And then hopefully you're prepared. And I think, by the way, these discussions and sessions like today are very useful for that, to just develop opinions and solutions and to trigger the discussion also in public.
Thank you. Do you have any specific numbers and the figures of each criteria? So you think that the 7% of VRE is that next step to be?
Yeah, well, this story I didn't develop myself. I took it over from the guy next to me. So maybe he can comment on the numbers.
But at least I will not comment the numbers. From my point of view, Peter said that you are on a good way, and the discussion and the presentations showed that the integration of a high share of renewable energies is possible, but you have to prepare several processes, you have to prepare the functions, and you have to prepare, of course, also the public discussion and the politicians. It's one of the biggest challenge, I think, to prepare the politicians for integration of renewables, big share of renewables. And maybe it's not good to discuss about 100% of renewables. Then you have to add what kind of 100% you are talking about. And maybe it is better to have a good portfolio of generation capacities where the renewable energies play a big role, absolutely high share of renewable energies in this portfolio. And then maybe it's easier to discuss also with the politicians about this question.
Well, from myself, I'd like to make two comments. Firstly, this time, the study on the grid stability is going to be continued, I believe. And what would be the sort of scenario, well, you're really going to assume? And then depending on that, well, the results could be quite different. For example, and it is working, and the interim report was just compiled, and a similar frequency drop, it was being assumed and analyzed, and 5 gigawatt, well, a loss of generation, what if? And then assuming some disaster in response to a Hokkaido incident, and they are really having a very strict sort of or the severe assumptions, and by having a linkage to that, and then from this perspective, you will get this one. And if you have this kind of comprehensive, multi-faceted perspectives, it will be better. And as we are going to see more of the higher integration of renewable energy, and it was not discussed, hydrogen is going to be another topic to be included, and then inclusive of that, we would be able to have the discussion on the more of the comprehensive roadmap, and then that would show us how we are really going to move ahead in terms of the energy is sort of the future, and that will give us a more at a high level perspective.
For the past 2 years, Renewable Energy Institute and other parties made a tremendous effort. Connect and manage concept was formulated. So in the unlikely event of disaster, connect and manage concept can be utilized. So this concept has been spread by institutes like RAY, and some progress has been made. But I think there is a further room for more efforts. In addition to that, going forward, we have to also focus on the responsibility of renewable energies. We have to define grid code that defines the responsibility of renewables. So going forward, we should focus on grid code in developing systems and grids going forward. Thank you. Connect and manage. The German participants, do you understand connect and manage? Maybe this is quite a special terminology. Could you explain briefly, Mr. Onishi? Yeah. Yeah, connect and manage is such that certain curtailment of output is to be accepted based on that condition. For example, system improvement doesn't have to be waited for. So you go ahead to connect to the grid, and within 1 to 3 years, grids will be developed, and the output curtailment will be achieved. In operating the system, maybe there will be a lot of lessons to be learned. In most cases, output curtailment can be achieved even lower level of curtailment. That is a connect and manage.
ございます。ではこの
Thank you. After the symposium, the reports, the two things that I would like to convey to you. First, have a discussion based on numbers, particularly in relation to renewables. In Japan, in Japanese, there are a lot of myth and misunderstanding. I think it was the case in Germany before, and unfortunately, they are groundless. They are without numbers, without evidence. I wouldn't say that they're flat wrong, but just old information, outdated information, obsolete. So have a discussion based on numbers this time. These were simulated results. Now, that's of most importance. If some of you are experts, well, Professor Tsuji, you talked about what about in this case? What about with this model? So maybe this model is not granular enough. You might have such opinions, but many people, different players, they do different simulations, they do different computations. What about the conditions, terms and conditions? What about the models? Having a discussion that would actually generate the good discussions in Japan and abroad. So discussions without numbers, this is really nothing other than rumors. I'm afraid of them. So I want many people to have discussions based on numbers, the blackout and more introduction of renewables. In those cases, we can have better, the productive discussions. That's one point. Second, why here in Japan, we see some difficulties introducing more renewable. It's been introduced, but not comparable to the international level. I think I can say this in one word. With all the rules, you can't introduce new technology. Grid code, Mr. Onishi talked about this already. The grid code. Those rules and laws and regulations. Dimitri, you talked about that. Regulations. Technologies, they are far ahead. So the laws and regulations have to catch up with them as soon as possible. Otherwise, you can't introduce new technology. Smartphones, AI, when people talk about it, if you are talking about abacus and very old-fashioned Professor Bell's telephone, you can't really discuss them. So you have to catch up with the new technology, how best they can be incorporated in the laws and regulations. The law or regulatory system can be the problem, not the technology. But in Europe and in Germany, 10 years, 20 years, you had those discussions. We should have more discussions on that point in Japan as well. Thank you.
Add one point. In my view, Japan should be a front runner. And I say this because I have the impression maybe Germany was a front runner in the past. But this energy transition is not now anymore a German energy transition, it's a global trend. And I would say even Germany is kind of starting to be slightly overpassed by other players. So be a front runner, which in my view mean you have installed in PV capacities over the last 5 years, which have made us jealous in Germany. I mean, 7, 8 gigawatt every year. We don't even install 2 gigawatt in Germany today. So continue this, but also be consistent. If you want really to be a front runner, you should also increase your targets. And it's what we show with our study. You can double the share of variable renewables without any problem. You can even triple them. So in my view, continue to increase your efforts, and maybe you will be the next front runner. And we, in Germany and Europe, will start also to think, oh yes, in Japan, given your constraints, you develop new solutions which make the transition a success.
ありがとうございます。太陽光発電確かにすごい入ったんです。
Thank you very much. It is true that we have a solar PV increase. However, wind power should make a catch up. So since that time has come, we would like to close the symposium at this point in time. and International Symposium, Renewables Integration into the Japanese Power Grid by 2030, a frequency study, and load flow analysis. And we are going to have a final version of the report to be uploaded on the website of RAY. Thank you very much.